Welcome to Quiet Universe, where we explore the most mysterious and awe-inspiring phenomena of the cosmos. Today, we're diving into the world of quasars, those brilliant, enigmatic beacons that light up the distant universe. These objects are not just visually stunning. They hold the key to some of the most profound questions in astrophysics, from their role in shaping galaxies to their connection with the supermassive black holes at their core. Quasars offer us a glimpse into the early universe and its dynamic evolution. In this video, we'll uncover how quasars form, what powers their immense energy, and how they've helped us understand the vast, ever-expanding universe. Whether it's their jets influencing intergalactic space or their use as cosmic lighthouses revealing distant galaxies, quasars are far more than just luminous points in the sky. So, sit back and let's journey together into the quiet, yet vibrant universe of quasars. Quasars are some of the most astonishing and powerful objects in the universe. Despite being relatively compact in size compared to galaxies, they shine with an intensity so immense that they can completely outshine the galaxies in which they reside. What makes them particularly remarkable is that their energy comes from supermassive black holes at the centers of galaxies millions or even billions of light years away. These black holes are unimaginably massive, with millions or even billions of times the mass of our Sun. The brilliance of a quasar is created by the enormous amounts of gas and dust swirling around the black hole in what's called an accretion disk. As this material spirals inward, it's heated to extreme temperatures, millions of degrees, by friction and the immense gravitational forces. This process releases an incredible amount of energy, which radiates out as light, X-rays, and other forms of radiation, creating that iconic, almost blinding luminosity we associate with quasars. One of the most fascinating things about quasars is how far away they are. When we look at a quasar, we're seeing light that left it billions of years ago, essentially looking back in time to the early universe. They offer a window into a period when galaxies were still forming and evolving. But quasars aren't just interesting for their brightness or distance. They had a profound impact on the galaxies they inhabit, shaping them with their intense radiation and gravitational forces. In many ways, quasars are not just isolated phenomena. They're part of the larger story of how the universe and its galaxies developed over time. Their existence reminds us just how dynamic and interconnected the cosmos really is. The light from a quasar can vary over time, flickering and changing in brightness. This variability, combined with their extreme distance, has led scientists to puzzle over their nature for decades. Before the true nature of quasars was understood, their strange and powerful emissions baffled astronomers, leading to speculation about what could produce such intense energy from such a compact source. In addition to their remarkable luminosity, quasars are also remarkable for their redshifts. A redshift occurs when the light from an object is stretched to longer, redder wavelengths as it moves away from us. The large redshifts observed in quasars indicate that they are receding from Earth at tremendous speeds, often approaching a significant fraction of the speed of light. This redshift is not just a measure of their velocity, but also a reflection of the expansion of the universe itself, with more distant quasars revealing the stretching of space-time over billions of years. Quasars are often found at the centers of galaxies that are undergoing periods of intense activity, often due to collisions or mergers with other galaxies. These interactions can funnel enormous amounts of gas and dust into the central black hole, triggering the quasar's brilliance. Over time, as the available fuel diminishes, the quasar's light fades, leaving behind a quieter galaxy with a dormant black hole at its core. There is a certain mystery in how these cosmic engines, so far removed from us in time and space, continue to captivate our understanding of the universe. Quasars are like cosmic lighthouses, their light guiding us to distant corners of the cosmos, providing clues about the early stages of the universe, and reminding us of the immense forces at play in the fabric of reality. Quasars are among the most captivating phenomena in the universe, each one harboring a supermassive black hole at its core. These black holes, often millions or even billions of times the mass of our Sun, sit at the heart of distant galaxies. While black holes themselves are invisible, the regions around them blaze with energy as matter spirals inward, pulled by their immense gravitational force. This process is what gives rise to the brilliance of quasars, causing them to outshine entire galaxies. The sheer brightness is staggering, so intense that even though quasars are located billions of light years away, we can see them from Earth. It's as if these ancient objects are piercing through time, giving us a glimpse of what the universe looked like in its early stages. The light we receive from quasars has often traveled billions of years across space, meaning we are observing them as they were long ago. In fact, many quasars are so distant that they formed when the universe was just a fraction of its current age, allowing us to peer into the cosmos' ancient past. The journey of their light, however, isn't straightforward. The expansion of the universe stretches the light waves emitted by quasars, a phenomenon known as redshift. This redshifting reveals their rapid movement away from us, providing valuable information about the universe's expansion rate and its large-scale structure. Each quasar is like a cosmic time capsule, offering insights into the early universe and the processes that shaped it. What's particularly mind-blowing is the scale of the energy emitted by quasars. They produce more energy in a small region than thousands of stars combined. This energy often manifests in the form of powerful jets of plasma, which can extend for millions of light-years from the quasar's core. These jets are accelerated to speeds close to the speed of light and carry enormous amounts of energy, interacting with the galaxy and the space around them. In some cases, these jets can blow away gas from the galaxy, regulating or even halting star formation, and thus playing a role in the galaxy's long-term evolution. Despite their size and power, quasars can also display variability in brightness, often over surprisingly short timescales. This variability is linked to changes in the flow of matter into the black hole, fluctuations in the accretion disk, or shifts in the intense magnetic field surrounding the black hole. These short bursts of brightness, sometimes lasting just a few days or months, highlight the dynamic and turbulent environment around the quasar, where forces of unimaginable scale play out in an area no larger than our solar system. At the heart of a quasar's incredible power is its accretion disk, a swirling vortex of gas, dust, and matter that spirals toward the black hole. As material in the disk moves closer to the event horizon, the point beyond which nothing can escape the black hole's gravity, it heats up due to friction and gravitational forces, releasing an enormous amount of energy in the form of light and radiation. This process is what powers the quasar's glow, making it one of the brightest objects in the universe. Yet, for all their brilliance, the true nature of quasars still raises profound questions about how black holes grow and evolve, and how they influence their surroundings. Perhaps one of the most fascinating aspects of quasars is their feedback on galaxy formation and evolution. The energy they emit doesn't just illuminate the cosmos. It actively shapes the galaxies that host them. Quasars can heat or expel gas from a galaxy, suppressing star formation and dramatically altering its structure. In some cases, their feedback can halt the formation of new stars altogether, leading to the quenching of the galaxy. This feedback mechanism is essential to understanding the life cycles of galaxies and how the universe has evolved over billions of years. In the grander cosmic landscape, quasars serve as beacons, shedding light on the distribution of matter in the universe. Their intense light can be used to map the cosmic web, the vast network of galaxies, gas, and dark matter that spans the universe. By studying the way quasar light is absorbed by intervening gas, astronomers can trace the large-scale structure of the universe and gain insights into the distribution of dark matter, one of the universe's most elusive components. In this way, quasars are not only remarkable in themselves, but also valuable tools for unlocking some of the most profound mysteries of the cosmos. In the chaotic early universe, quasars began to form not long after the Big Bang, emerging from an environment brimming with dense gas and turbulent matter. These extraordinary objects are powered by supermassive black holes that, against what might seem possible, already existed in the young universe. The mystery lies in how these black holes grew so quickly, reaching millions or even billions of times the mass of our sun in such a brief period. For this rapid growth, the universe provided an ideal setting: regions dense with gas and matter that fed these black holes at high rates. The material spiraling into the black hole formed an accretion disk, and the intense gravitational forces at play converted this infalling matter into enormous amounts of energy, leading to the dazzling brightness we associate with quasars. Despite being so young, these quasars were incredibly luminous, shining across vast cosmic distances. Their light reaches us only after traveling billions of years, offering a glimpse into a time when the universe was just a fraction of its current age. These early quasars were often linked to the formation and mergers of galaxies, as the violent interactions of galaxies colliding could provide the necessary fuel to power the growing black holes. In this way, Quasars are thought to be integral to the very process of galaxy formation itself. Quasars also played a crucial role in one of the universe's most significant events, the reionization of the cosmos. The intense radiation they emitted helped ionize the intergalactic medium, marking the end of the so-called cosmic dark ages. Their powerful outflows of energy and material had profound impacts on the surrounding cosmic environment, influencing the formation of stars, galaxies, and the structure of the universe on a large scale. But our understanding of these early quasars is still limited. Observing them is incredibly challenging due to the immense distances involved and the effects of redshift, which stretch the light from these quasars into longer wavelengths as they move away from us. Nevertheless, the faint signals we do detect tell a fascinating story of a universe in the throes of its formative years, shaped in part by these brilliant, enigmatic objects. At the heart of every quasar lies a supermassive black hole, a gargantuan entity with a mass billions of times that of our Sun. It is the very engine driving the quasar's brilliance. But what makes these black holes so extraordinary is not just their size, but their ability to convert the raw forces of gravity into light and energy on a scale unmatched by anything else in the universe. The process begins with the black hole's immense gravitational pull, which draws in vast amounts of gas, dust, and even entire stars from its surroundings. As this matter spirals inwards, it forms a swirling disk known as an accretion disk, where material heats up to millions of degrees as it approaches the event horizon. This intense heat causes the disk to glow across the electromagnetic spectrum, producing the radiant light that we see from quasars, outshining entire galaxies in the process. The accretion disk is more than just a collection of orbiting material. It's where the black hole's gravity works its most transformative magic. The infall of matter releases incredible amounts of energy, as gravitational potential energy is converted into radiation. This process is staggeringly efficient, far surpassing the energy output of nuclear fusion, making quasars some of the brightest objects in the cosmos. But the black hole doesn't just passively consume matter. In some cases, high-speed jets of particles are ejected from the poles of the black hole, moving at nearly the speed of light. These relativistic jets, while still a mystery in many respects, are believed to form due to magnetic fields twisted by the intense rotation of the accretion disk. These jets can stretch across millions of light years, carving through galaxies and influencing the distribution of matter on a cosmic scale. Supermassive black holes also regulate the brightness of quasars, which can vary over surprisingly short timescales, days, months, or years. This variability is closely tied to the flow of material onto the black hole, as fluctuations in the accretion rate can cause changes in brightness. While the processes behind this variability aren't fully understood, it suggests that quasars are not static but dynamic, with shifts in their surrounding environment influencing their energy output. These shifts can give astronomers clues about the nature of the accretion process and the behavior of matter under extreme gravitational forces. The influence of supermassive black holes extends beyond just powering quasars. Their activity can shape the very galaxies they inhabit. The enormous energy and outflows from a quasar can heat and expel gas from its host galaxy, potentially halting star formation and altering the galaxy's evolution. This feedback mechanism means that the black hole's growth and the galaxy's development are deeply intertwined, with the black hole sometimes acting as a regulating force on the galaxy's future. Another fascinating aspect of supermassive, despite all we know, many questions remain unanswered. One of the most puzzling is how these black holes in the early universe grew so rapidly. The fact that we see supermassive black holes just a few 100 million years after the Big Bang suggests a growth process far more efficient than any current models can fully explain. Did they form from the collapse of massive primordial stars? Were there special conditions in the early universe that allowed black holes to grow faster than we see today? These are questions that still challenge astronomers and push the boundaries of our understanding of cosmic evolution. In the end, the role of supermassive black holes and quasars is not just about devouring matter and producing light. They are architects of galaxies, regulators of cosmic energy flows, and key players in the story of how the universe came to be as we see it today. The forces they wield are as mysterious as they are powerful, and studying them brings us closer to unraveling the most fundamental questions of our universe. Quasars are among the most energetic and enigmatic objects in the universe, powered by the immense gravitational forces surrounding supermassive black holes. When matter is drawn towards a quasar's central black hole, it spirals inward in a process known as accretion. This gravitational pull isn't simply the matter falling inward. It's an intense interaction that accelerates particles to extreme speeds. The energy generated as matter is pulled into tighter orbits causes friction and immense heat, creating a phenomenon where gravitational energy is transformed into radiant energy. This energy escapes as powerful electromagnetic radiation, lighting up the quasar and making it visible across billions of light years. The energy produced by quasars is extraordinary because their accretion disks, swirling disks of gas, dust, and other material, heat up to millions of degrees. The intense heat, combined with rapid movement, causes the disk to glow brightly, producing emissions that span the entire electromagnetic spectrum, from radio waves to X-rays and gamma rays. This radiation doesn't emerge from the black hole itself, but from the matter heated to such extreme temperatures that it radiates energy at all wavelengths. For those close enough to observe this energy, like us from Earth with the help of telescopes, the sheer variety of emissions is staggering. What's more captivating, though, is the presence of relativistic jets. These jets shoot out from the poles of quasars, streams of plasma moving at nearly the speed of light. They don't just travel in a straight line. These streams are shaped by the incredibly powerful magnetic fields that surround the black hole, pushing and accelerating particles at near-light speeds in two opposing directions. It's almost like witnessing a cosmic fire hose, but on a scale too vast to truly comprehend. The energy released through these jets isn't just raw speed. A process called synchrotron radiation occurs, where particles spiraling in the magnetic field emit radio waves and other forms of radiation. These emissions can extend for hundreds of thousands of light years, creating vast lobes of energized material far from the quasar itself. The magnetic fields, although invisible, are critical to this whole process, shaping the direction and intensity of these jets. The interaction between the inflowing material and the radiation produced near the black hole is complex. Infalling gas and dust can either be heated until it radiates away its energy or swept up in the jets and ejected from the region altogether. This tug-of-war between forces keeps the quasar in a state of flux, where its energy output can vary based on how much matter is falling into the black hole at any given time. It's almost like a living system, constantly adjusting to its environment. What makes quasars especially fascinating is how efficiently they convert matter into energy. In many ways, they are far superior to processes like nuclear fusion that power stars. A small amount of mass in a quasar's accretion disk can release tremendous amounts of energy, often more than an entire galaxy. Despite their intense power, quasars aren't steady beacons. Their energy output can fluctuate dramatically depending on the rate at which matter is consumed by the black hole. This variability gives each quasar its own unique personality, with some growing brighter or dimmer over the course of months or years. For astronomers, observing these changes feels like watching the behavior of a distant, unpredictable giant. The discovery of high-redshift quasars has opened a portal into a time when the universe was in its infancy, less than 1 billion years after the Big Bang. These quasars, with redshifts greater than 7, offer a rare glimpse into the distant past, revealing an era when the cosmos was still a place of rapid formation and transformation. Their redshift is a key indicator of how far away they are, and how long their light has been traveling to reach us, more than 13 billion years in some cases. It's a kind of cosmic archaeology, where light from these quasars provides insight into a time we can never physically visit, but can observe through the faint glow of these distant beacons. Finding such distant quasars is no simple task. Advanced telescopes, like those involved in deep sky surveys, have to look far beyond the familiar stars and galaxies to detect the faint, almost ghostly light of quasars that have been traveling across the universe for nearly its entire history. The challenge is immense, as the farther away a quasar is, the fainter it appears, stretched thin across space by the universe's expansion. Astronomers have to filter through countless other cosmic objects, sorting through the noise of stars, galaxies, and dust to identify these rare, high-redshift quasars. Their faintness, combined with their distance, requires not only powerful equipment but also careful analysis to pinpoint their signatures. Yet, when these distant quasars are found, they become invaluable tools for studying the conditions of the early universe. By examining their light, astronomers can piece together what the universe looked like when it was just a fraction of its current age. High-redshift quasars illuminate the epoch of reionization, a period when the first stars and galaxies began to ionize the cold, neutral hydrogen gas that filled the universe. This transition was crucial in shaping the structure of the universe as we know it, and quasars serve as cosmic lighthouses that pierce through this foggy, transformative epoch. The existence of such quasars raises profound questions about the formation of supermassive black holes in the early universe. These quasars are powered by black holes with masses hundreds of millions, or even billions, of times that of the Sun. How could such enormous black holes form so soon after the Big Bang, when the universe was still young? Their very existence challenges our understanding of black hole formation, as conventional theories struggle to explain how they could have accumulated so much mass so quickly. These early supermassive black holes may have been seeded by the collapse of massive clouds of gas, or perhaps formed through the mergers of smaller black holes, but the details remain one of the great mysteries of modern astrophysics. Spectral analysis of these high-redshift quasars reveals not just the black hole at their core, but also the surrounding intergalactic medium. By studying the absorption lines in the quasar spectrum, astronomers can deduce the chemical composition of the gas between galaxies. This early intergalactic medium was far simpler than what we see today, consisting mostly of hydrogen and helium, with only trace amounts of heavier elements. These observations provide a snapshot of the universe's chemical evolution, showing how the first stars and galaxies began enriching the cosmos with heavier elements forged in their cores. High-redshift quasars also give us critical insights into the formation of early galaxies and cosmic structures. The light from these quasars passes through the filaments of gas and galaxies that make up the cosmic web, allowing astronomers to map out the large-scale structure of the universe when it was still forming. The interplay between quasars, galaxies, and intergalactic gas reveals the complex processes that shaped the universe's development, from the birth of the first stars to the emergence of massive galaxies. Each discovery of a high-redshift quasar brings with it a wealth of information about the universe's earliest moments, offering clues that refine our understanding of how everything we see today came into being. These quasars are more than just distant, ancient objects. They are messengers from a time long gone, delivering whispers of the universe's most formative years. Quasars, some of the brightest objects in the universe, serve as perfect background sources for one of nature's most intriguing phenomena: gravitational lensing. When the light from a distant quasar passes through the gravitational field of a massive object like a galaxy or galaxy cluster, the quasar's light is bent and distorted by the intervening mass. It's like seeing the universe through a cosmic magnifying glass, but with much more dramatic effects. The quasar's light, instead of traveling in a straight line, is redirected by the curvature of space-time caused by the massive foreground object, creating multiple images of the quasar, or stretching its light into arcs. This bending of light can lead to the formation of 2, 4, or even more images of the same quasar, depending on the alignment between the quasar, the lensing object, and Earth. What's truly extraordinary is that these multiple images may not all appear simultaneously. Because each light path has a slightly different distance to travel and may pass through regions of differing gravitational intensity, some of the images can be delayed by days, months, or even years. Observing these time delays between the various images is crucial for understanding both the quasar and the intervening lens, as well as for making precise measurements of cosmic distances. Gravitational lensing doesn't just bend light. It can also magnify the quasar's brightness. Massive galaxies in the foreground can act as lenses, increasing the apparent luminosity of the distant quasar by factors of 10 or more. For astronomers, this magnification is a valuable tool. Not only does it allow them to study quasars that might otherwise be too faint to observe, but it also offers an opportunity to measure the mass of the intervening object that is acting as the lens. By analyzing how much the quasar's light is bent and magnified, researchers can estimate the mass of the galaxy or galaxy cluster that lies in the quasar's path. Quasar lensing is also an important method for probing the distribution of dark matter. Since dark matter doesn't emit light but has mass, it can bend light just like visible matter does. When a quasar's light is distorted, the pattern of the distortion reveals where the mass is located, even if that mass is invisible. In this way, lensed quasars allow scientists to map out dark matter's presence in galaxies and clusters, helping to unravel its otherwise elusive nature. The effect of lensing has also been pivotal in the discovery of high-redshift quasars. The magnification of their light by intervening galaxies makes these distant objects easier to spot, even when they are billions of light-years away. Without this natural cosmic boost, some of the most distant quasars might have remained hidden from our view, locked behind the veil of their enormous distances. But thanks to gravitational lensing, astronomers have been able to detect quasars that date back to some of the earliest epochs of the universe. Microlensing, where individual stars or smaller objects in the foreground galaxy act as lenses, adds yet another layer of complexity and opportunity. When microlensing occurs, the quasar's light can flicker or change in brightness over short timescales, revealing incredibly fine details about the quasar's internal structure. This flickering allows astronomers to study regions of the quasar that would otherwise be impossible to resolve, such as the accretion disk around its supermassive black hole or the inner edges of its relativistic jets. Microlensing is like zooming in on the quasar's inner workings through a natural, cosmic telescope. The study of lensed quasars also plays a critical role in refining our understanding of the universe's expansion rate. By measuring the time delays between the multiple images of a quasar and modeling the gravitational lensing effects, astronomers can determine the distance to both the quasar and the lensing galaxy with high precision. These measurements contribute to more accurate estimates of the Hubble constant, the rate at which the universe is expanding. Lensed quasars, therefore, are not only fascinating cosmic phenomena in their own right, but are also crucial to refining the larger framework of cosmology. In a way, gravitational lensing transforms quasars from distant, isolated objects into complex systems that help reveal the underlying structure of the universe. Every bent light path, every time delay, and every magnified quasar image contains clues about the hidden mass between us and the quasar, offering a deeper understanding of everything from dark matter to the fundamental forces shaping cosmic evolution. Quasars, with their extraordinary brightness, serve as cosmic lighthouses, shining across vast distances and illuminating regions of the universe that would otherwise remain dark and mysterious. Their light travels across billions of light years, passing through countless gas clouds, galaxies, and clusters on its way to us. This journey allows quasars to act as natural probes, revealing the structure and composition of the universe's most remote regions. By studying the light from quasars, we can uncover clues about the state of the universe long before our own galaxy even formed. One of the most valuable ways astronomers use quasars is to study the intergalactic medium, the vast stretches of gas that exist between galaxies. As quasar light passes through this gas, it leaves behind subtle imprints in the form of absorption lines. Each absorption line corresponds to a specific element or molecule, providing a detailed chemical fingerprint of the matter that lies between galaxies. These absorption lines reveal not only the composition, but also the temperature and density of the gas, offering a window into how the universe evolved from a sea of neutral hydrogen into the complex web of galaxies we see today. The light from quasars doesn't just interact with intergalactic gas. It also passes through the outer regions, or halos, of galaxies, revealing their structure and composition. These galaxy halos are difficult to observe directly, but quasars help to illuminate them by acting as background light sources. When quasar light passes through a galaxy halo, it reveals the presence of gas and dark matter, giving astronomers insights into how galaxies are structured on their outskirts and how they interact with the surrounding environment. By analyzing the absorption lines in quasar spectra, astronomers can also infer the chemical composition of early galaxies. As quasar light passes through these galaxies, it picks up information about the metals and elements present within them. This is particularly important for understanding how the first stars and galaxies enriched the universe with heavier elements. These observations provide a record of the gradual buildup of chemical complexity over billions of years, offering clues to how galaxies formed, grew, and evolved into the massive structures we see today. Quasars also play a crucial role in mapping the large-scale structure of the universe. As their light passes through cosmic filaments and clusters of galaxies, it traces out the vast web of matter that connects galaxies across the universe. This cosmic web is the scaffolding upon which galaxies are built, and quasars provide a way to map its structure and see how it evolved over time. By tracking how quasar light is absorbed or distorted by these filaments, astronomers can reconstruct the three-dimensional distribution of matter in the universe, revealing the underlying architecture of cosmic structures. Additionally, quasars offer unique insights into the formation and evolution of galaxies. By studying how quasar light interacts with the gas surrounding galaxies, astronomers can trace how galaxies gather material over time, feeding their central black holes and fueling star formation. These observations help us understand how galaxies grow from small, early structures into the massive systems we see today. Quasars are also invaluable for studying galaxy mergers, as their light can reveal the chaotic environments where galaxies collide and blend into new, larger formations. One of the most profound uses of quasars is in tracing the distribution of dark matter. While dark matter is invisible, its gravitational influence bends quasar light, subtly distorting the images we see from Earth. By analyzing these distortions, astronomers can map out the distribution of dark matter in and around galaxies. This information is critical for understanding how galaxies are held together and how dark matter shapes the large-scale structure of the universe. Quasars also help shed light on the reionization period of the early universe, a crucial era when the first stars and galaxies began to ionize the neutral hydrogen gas that filled the cosmos. The light from high-redshift quasars allows astronomers to observe this epoch directly, revealing how the universe transitioned from a dark, neutral state into the bright, star-filled universe we see today. By studying the quasar light that passes through partially ionized gas, we can piece together how this transformation unfolded. In cases where quasars are gravitationally lensed by foreground galaxies, they provide a means of identifying distant, otherwise invisible galaxies. The quasar's light can be bent and magnified by the gravitational field of these galaxies, making it possible to detect and study faint objects that would normally be too distant or too dim to observe. These lensed quasars act as cosmic flashlights, revealing hidden structures and distant galaxies that lie far beyond the reach of our telescopes. Quasars are also essential tools for measuring cosmic distances. Because their light travels so far, they can be used as reference points for measuring the expansion of the universe. By studying how the light from distant quasars is redshifted, stretched to longer wavelengths, we can determine how fast the universe is expanding and refine estimates of the Hubble constant. Quasars help us trace the evolution of the universe's expansion from its rapid early phases to its current, more gradual rate. Through their vast distances and extraordinary brightness, quasars serve as sentinels of the cosmos, providing a constant stream of information about the universe's distant past and its fundamental structure. They are more than just brilliant points of light. They are messengers from the farthest reaches of space, illuminating the intricate and dynamic processes that shaped the universe into what it is today. Quasar jets are among the most powerful forces in the universe, stretching thousands of light-years out into intergalactic space, far beyond their host galaxies. These jets carry immense amounts of energy away from the quasar's central black hole, spewing out plasma at near-light speeds. The jets are launched from regions close to the black hole, where intense magnetic fields and the spinning accretion disk twist and accelerate matter outward. This process ejects particles in tightly focused beams, which cut across intergalactic space, leaving a lasting imprint on their surroundings. As these jets plow through space, they have profound effects on nearby galaxies. One of their surprising influences is on star formation. In some cases, the energy and turbulence from quasar jets can compress gas in nearby galaxies, triggering bursts of star formation. However, in other situations, the jets can have the opposite effect. Their immense heat and force can sweep away or heat up the gas in the vicinity, preventing it from collapsing to form stars. This delicate balance means that quasar jets can either nurture or suppress the birth of stars, depending on the specific conditions they encounter. Beyond affecting individual galaxies, quasar jets can displace and heat the intergalactic gas they pass through. This is no minor disturbance. The jets inject so much energy into the gas that it can prevent it from cooling and collapsing into new galaxies. The heat from these jets keeps the gas in a diffuse, hot state, regulating the growth of the quasar's host galaxy as well as other galaxies in the region. Without this feedback, the host galaxy might grow unchecked, becoming much larger and denser. In this way, quasar jets act as cosmic regulators, maintaining a balance between growth and stability in the galaxies they influence. As these jets travel through space, they create massive radio lobes, enormous structures filled with energetic particles that can be detected from Earth as radio emissions. These lobes, sometimes hundreds of thousands of light-years across, are a striking visual reminder of the power of quasar jets. The lobes show where the jets have deposited their energy, creating vast bubbles of hot plasma that remain visible long after the quasar itself has quieted down. These radio lobes are not just remnants of explosive activity. They are key to understanding the interaction between quasar jets and their surroundings. Quasar jets also play a role in generating magnetic fields in intergalactic space. As the jets push through the thin gas between galaxies, they stir up the plasma, creating turbulence that can amplify existing magnetic fields or even generate new ones. These magnetic fields, though weak, can influence the behavior of charged particles over vast distances, shaping the dynamics of intergalactic space and affecting the movement of gas and dust between galaxies. The influence of quasar jets doesn't stop at individual galaxies or gas clouds. They also play a part in triggering or suppressing galaxy mergers. By injecting energy into the surrounding environment, jets can either destabilize galaxies, causing them to merge, or they can keep galaxies apart by blowing out gas that would otherwise act as gravitational glue. Galaxy mergers are key events in the universe, reshaping galaxies and triggering new rounds of star formation, and quasar jets can either encourage or hinder this process, depending on how they interact with the galaxies involved. On an even larger scale, quasar jets affect the structure of the universe itself through feedback mechanisms. By regulating the amount of gas available for star formation and galaxy growth, they contribute to the formation of large-scale cosmic structures, such as galaxy clusters and superclusters. These jets can also influence the temperature and distribution of intergalactic gas, altering the way matter is distributed throughout space. This feedback, in turn, helps shape the overall architecture of the universe, with quasar jets playing a key role in determining how galaxies and galaxy clusters evolve over billions of years. In short, quasar jets are not just explosive phenomena confined to their host galaxies. They extend their influence across vast distances, shaping the intergalactic environment, regulating the growth of galaxies, and even playing a role in the cosmic web that connects galaxies across the universe. Their reach is both direct and indirect, a testament to the enormous energy released by these cosmic powerhouses. Through their interaction with gas, galaxies, and magnetic fields, quasar jets leave a lasting imprint on the universe, altering the very fabric of cosmic evolution. Quasars, with their extreme brightness and distant locations, are among the most powerful tools astronomers have for probing the elusive nature of dark matter. These cosmic beacons shine brighter than entire galaxies, making them visible across vast distances, even from billions of light-years away. Their light has traveled across the universe, encountering and interacting with various structures along the way, which provides unique opportunities to study dark matter. One of the most significant ways quasars help in this quest is through gravitational lensing. As their light passes by massive objects like galaxies or galaxy clusters, it is bent and distorted due to the gravitational influence of both visible matter and dark matter. This lensing effect creates multiple images of the quasar, as well as arcs or rings of light, which reveal the distribution of dark matter in the intervening objects. Gravitational lensing is not just about creating beautiful visual effects. It's a precise scientific tool. By studying the degree of distortion in the quasar's light, astronomers can infer how much mass, including dark matter, lies between the quasar and Earth. Since dark matter does not emit light, its presence can only be detected through its gravitational pull. Quasars, therefore, act like cosmic flashlights, highlighting the invisible dark matter that permeates the universe. The patterns of lensing tell us about the clumps and filaments of dark matter that stretch between galaxies, providing a map of where this unseen substance resides. Quasar spectra, essentially the breakdown of the quasar's light into its component wavelengths, are another key tool in understanding dark matter. As light travels through the universe, it passes through the intergalactic medium, the thin gas that fills the space between galaxies. Dark matter plays a role in shaping this medium, and by examining the absorption lines in a quasar spectrum, astronomers can detect the influence of dark matter on the distribution of gas. These absorption lines provide a snapshot of the gas and dark matter filaments that make up the cosmic web, the vast interconnected structure that binds the universe together. Through these studies, quasars help to trace the invisible scaffolding of dark matter that underpins galaxy formation and evolution. The gravitational fields around quasars themselves, particularly those with supermassive black holes at their centers, also contribute to our understanding of cosmic structures. The intense gravity near a quasar bends light from other sources behind it, creating a lensing effect that provides additional insights into the distribution of mass, including dark matter. This bending of light allows astronomers to study not only the quasar's host galaxy, but also the surrounding environment and the dark matter that shapes it. By measuring how quasar light is altered, we gain clues about the mass and structure of both nearby galaxies and more distant objects. Quasars are powered by supermassive black holes, which sit at the centers of galaxies. These black holes are surrounded by accretion disks of matter spiraling inward, releasing enormous amounts of energy as they fall into the black hole. This energy, which makes quasars so luminous, is also a key to understanding how dark matter interacts with galaxies. The gravitational influence of dark matter helps shape the growth of galaxies and can regulate how material is funneled into the central black hole. Observing the behavior of quasar jets, streams of particles ejected at nearly the speed of light, can reveal how dark matter structures influence the movement of gas and other matter in the universe. Another remarkable feature of quasars is their variability in brightness. Over time frames ranging from days to decades, quasars can flare up or dim, a behavior influenced by the activity around their supermassive black holes. This variability gives astronomers a way to study the environments in which quasars reside, including the dark matter that helps structure those environments. The interplay between a quasar's energy output and the dark matter around it provides clues about the complex relationship between dark matter, galaxies, and the supermassive black holes at their centers. Quasar jets can extend for millions of light years, reaching far beyond their host galaxies into intergalactic space. These jets interact with both the visible and dark matter around them, and by studying the jet's behavior, astronomers gain insights into how dark matter affects the large-scale structure of the universe. Jets can also illuminate regions of space that would otherwise remain hidden, highlighting the presence of dark matter and offering a way to trace its influence across vast distances. By observing how these jets influence the gas and dark matter in their path, astronomers can better understand the role of dark matter in shaping cosmic structures. Quasars existed in the early universe, providing crucial information about the formation and evolution of the cosmos. They were active during a time when galaxies were still forming, and the dark matter that surrounded them was helping to shape these young structures. Studying quasars from this early period gives us a glimpse into the conditions that prevailed shortly after the Big Bang, offering clues about how dark matter influenced the early stages of galaxy formation. The light from these ancient quasars carries information from a time when the universe was still young, and analyzing this light allows us to piece together the history of dark matter's role in cosmic evolution. The immense energy emitted by quasars is fueled by the accretion disks that surround their central black holes. These disks are formed as gas and other materials spiral inward, releasing gravitational energy as they are pulled toward the black hole. The interaction between this energy and the surrounding dark matter helps to shape the quasar's environment and regulate the flow of material into the black hole. By studying how this energy interacts with dark matter, astronomers can learn more about the complex relationship between the visible and invisible components of the universe. In the end, quasars provide one of the most powerful ways to study dark matter. Their light, their jets, their gravitational influence all serve as tools for unraveling the mysteries of this invisible but essential part of the universe. Through quasars, we gain a deeper understanding of how dark matter shapes the cosmos, influences galaxy formation, and holds the universe together in ways we are only beginning to understand. Quasars, with their immense power, have a profound impact on the galaxies that host them, reshaping their evolution over cosmic time. At the heart of this influence are the powerful winds driven by quasars, which eject enormous amounts of gas from galaxies. These winds, launched from the central regions near the supermassive black hole, carry energy outward at speeds that can reach thousands of kilometers per second. As they blast through the galaxy, they sweep away the cold gas that is essential for star formation, effectively starving the galaxy of the raw material needed to form new stars. The result is a galaxy that struggles to sustain the creation of new stars, profoundly altering its evolutionary path. Quasars are capable of regulating star formation in multiple ways, not only by expelling gas, but also by heating it. The energy radiated by a quasar heats the surrounding gas, making it difficult for the gas to cool and collapse into new stars. This heating process can temporarily halt star formation, leading to periods of dormancy in the galaxy's life cycle. Over time, this intermittent suppression of star formation can shape the galaxy's structure and determine how it grows. In some cases, the intense energy output from the quasar can halt star formation entirely, transforming a once active galaxy into what astronomers call a quenched galaxy, where star formation ceases altogether. This quenching process is a critical aspect of galaxy evolution, as it marks the transition from youthful, star-forming galaxies to older, more passive ones. The feedback from quasars, the combined effects of their winds, radiation, and jets, can also influence the overall size and shape of galaxies. When quasars eject gas, they can strip the outer layers of a galaxy, reducing its size or flattening its structure. Alternatively, the force of quasar-driven winds can trigger bursts of star formation in localized regions, potentially reshaping the galaxy's internal structure by igniting new clusters of stars. This dynamic interaction between quasar activity and galactic gas creates a push and pull effect that continuously sculpts the galaxy over millions of years. The very structure of a galaxy, from its bulging core to its elongated arms, can be traced back to the influence of quasar feedback at various points in its history. Beyond their impact on star formation, quasars play a role in the behavior of galactic halos, the outer regions of galaxies that contain not just stars and gas, but also dark matter. The energy emitted by quasars can affect the distribution of dark matter in these halos by altering the gravitational dynamics of the galaxy. As the quasar's energy heats and displaces gas, it can change how dark matter is distributed within the halo, potentially reshaping the galaxy's overall mass and gravitational pull. This interplay between dark matter and quasar feedback highlights how deeply quasars are intertwined with the fundamental processes that govern galaxy evolution. Quasars are often found in galaxies that are undergoing mergers, suggesting a close link between quasar activity and galaxy evolution during these violent cosmic events. When two galaxies merge, the gravitational interactions between them can funnel gas toward the central black hole, fueling a quasar. The energy released by the quasar in turn affects the newly merged galaxy, driving out gas and reshaping its structure. These mergers can lead to the formation of massive elliptical galaxies, and quasars play a key role in regulating how these new galaxies form. By both fueling black hole growth and expelling gas, quasars act as both destroyers and creators in the chaotic environments of merging galaxies. In some cases, quasar jets, which extend far beyond the host galaxy, can have unexpected effects on neighboring galaxies. As these jets move through intergalactic space, they can compress gas in nearby galaxies, triggering new waves of star formation. The pressure exerted by the jets acts like a cosmic spark, igniting regions of gas that would otherwise remain dormant. This process reveals how quasars, though centered in one galaxy, can reach across vast distances to influence the formation of stars in completely different galaxies. This intergalactic influence underscores the far-reaching impact of quasars on the universe's broader ecosystem. Quasars are closely tied to the growth of supermassive black holes, which sit at the center of most galaxies. As gas and matter fall into the black hole, they fuel the quasar, driving its enormous energy output. In this way, quasars are both a product of black hole growth and a regulator of it. The process of accreting gas into the black hole is chaotic and often results in the expulsion of much of the gas through powerful winds and jets. This self-regulating mechanism ensures that the black hole doesn't grow unchecked, as the quasar's energy limits the amount of matter that can fall into the black hole at any given time. The influence of quasars also extends beyond their host galaxies and into the intergalactic medium. As quasars emit energy, they enrich the surrounding space with heavy elements produced during star formation. These elements are carried outward by quasar winds, seeding the intergalactic medium with the building blocks needed for future generations of stars and galaxies. This enrichment process contributes to the chemical evolution of the universe, spreading elements like carbon, oxygen, and iron far beyond the galaxies where they were formed. Quasars may have also played a pivotal role in the reionization of the early universe, a critical phase in cosmic history when the first galaxies and stars began to ionize the neutral hydrogen that filled the cosmos. The intense ultraviolet radiation emitted by quasars helped to reionize vast regions of space, transforming the early universe from a dark, opaque environment into the bright, transparent one we see today. By studying distant quasars, astronomers gain insights into how this reionization process unfolded and how quasars contributed to the dawn of the modern universe. In all these ways, quasars are not just brilliant beacons lighting up the distant cosmos. They are powerful forces that have shaped the history and evolution of galaxies. Their influence stretches from the smallest scales, affecting star formation and gas dynamics within individual galaxies, to the largest scales, impacting the evolution of the universe as a whole. Through their energy output, feedback mechanisms, and interactions with dark matter, quasars are key drivers of cosmic evolution, leaving an indelible mark on the galaxies they inhabit and the universe beyond. Quasar feedback is a powerful and dynamic process that has a significant impact on the ability of galaxies to form new stars. At the core of this phenomenon are the outflows of gas that quasars can drive, which move at incredible speeds, sometimes reaching thousands of kilometers per second. These outflows, generated by the energy released from the supermassive black holes at the center of galaxies, can strip away the gas that would otherwise fuel star formation. Without this gas, the galaxy is left barren, unable to sustain the cycle of birth and death that stars undergo. The violent expulsion of this material represents a crucial phase in the life of a galaxy, one where it is effectively starved of the resources necessary to continue growing. The interstellar medium, the space within galaxies filled with gas and dust, also feels the effects of quasar feedback. As the energy from a quasar heats this medium, the gas becomes too hot to cool and collapse into stars. Star formation is a delicate process that requires cool, dense clouds of gas to condense under gravity, but quasar-driven heating makes this nearly impossible. This disruption of the cooling process can delay or even prevent new stars from forming for long periods of time. The inability of gas to cool sufficiently can create large, starless regions in galaxies, halting the natural growth that would otherwise populate the galaxy with new stars. Quasar feedback doesn't just heat gas. It can also create shock waves that ripple through a galaxy. These shock waves compress and reshape the gas within the galaxy, sometimes creating denser regions where stars might form, but often dispersing the star-forming material altogether. These shock waves can be powerful enough to drive gas out of the galaxy entirely, ejecting it into intergalactic space where it becomes even less likely to contribute to star formation. The balance between compression and dispersal determines whether feedback will momentarily boost star formation or suppress it entirely. One of the most direct ways quasar feedback suppresses star formation is through the ionization of gas. The intense radiation emitted by a quasar can strip electrons from atoms, ionizing the gas and making it difficult for the gas to collapse under its own gravity. Ionized gas is highly energized and unstable, resisting the compression needed to form stars. This process can effectively sterilize large regions of a galaxy, preventing any new stars from forming until the quasar's activity wanes, or the gas has time to cool and recombine. The reach of quasar feedback extends beyond individual galaxies and can influence entire clusters of galaxies. As quasar-driven outflows escape from their host galaxy, they interact with the surrounding galaxies within a cluster. The impact of these outflows can ripple through neighboring galaxies, suppressing star formation across multiple systems simultaneously. By altering the gas dynamics on such large scales, quasar feedback can regulate the growth of entire galaxy clusters, determining the rate at which new stars form and shaping the evolution of these massive cosmic structures. In some cases, the long-term effects of quasar feedback can lead to a phenomenon known as galaxy quenching. When a galaxy is quenched, star formation is permanently or semi-permanently halted. This can happen when quasar feedback expels so much gas, or heats it to such an extent that the galaxy can no longer sustain the conditions needed for star formation. Quenched galaxies are often older and more passive, with little to no new star formation occurring. Quasar feedback is a key driver in transitioning galaxies from active, star-forming systems to these quieter, quiescent states. Interestingly, the suppression of star formation due to quasar feedback isn't just a localized or small-scale process. It can be observed across vast cosmic distances. The effects of quasar feedback are so powerful that they can be detected in galaxies that are billions of light-years away from Earth. Observations of distant galaxies show clear signs of gas being heated, ionized, or expelled by quasar activity, providing direct evidence of how these feedback mechanisms shape galaxies on both large and small scales. There is also a more complex interplay between quasar activity and star formation. In some cases, before quasar feedback suppresses star formation, it can actually trigger short-lived bursts of star formation. The compression of gas by quasar-driven shock waves, or jets, can lead to pockets of dense gas that rapidly form new stars. However, this burst of star formation is often temporary, as the sustained outflows from the quasar eventually expel or heat the remaining gas, leading to an overall suppression of star formation. The regulation of supermassive black hole growth is also closely tied to quasar feedback. As gas is accreted onto the black hole, it powers the quasar, which in turn drives the feedback mechanisms that influence the surrounding galaxy. This process is self-regulating. Too much accretion fuels stronger feedback, which can then halt further gas inflow and slow the growth of the black hole. In this way, quasar feedback acts as a natural brake on black hole growth, preventing runaway accretion that could destabilize the host galaxy. This intricate balance ensures that both the black hole and its host galaxy evolve together in a symbiotic relationship. Through these processes, quasar feedback plays a crucial role in shaping galaxies, regulating star formation, and ensuring that the growth of both stars and black holes proceeds in a controlled, balanced manner. This feedback is not just a byproduct of quasar activity. It is an essential mechanism that governs the long-term evolution of galaxies across the universe. When galaxies merge, the resulting cosmic collisions often set the stage for the birth of quasars, some of the brightest and most energetic objects in the universe. During these mergers, immense gravitational forces funnel vast amounts of gas and dust toward the center of the merging galaxies, where it feeds the supermassive black hole residing at the core. This sudden influx of material rapidly accelerates the black hole's growth and ignites quasar activity, turning the central region of the galaxy into a beacon that outshines the combined light of all the stars within the galaxy. Mergers are chaotic, but in their turbulence, they often trigger intense periods of star formation, known as starbursts. These starbursts occur as gas clouds collide and compress, birthing new stars at a furious rate. However, this burst of star formation is often followed by a quasar phase. As the gas that didn't form stars continues to spiral inward toward the central black hole, it fuels the quasar, creating an environment where both star formation and black hole accretion can coexist for a brief time before quasar feedback halts further star production. The transition from a starburst to a quasar marks a key evolutionary stage in the life cycle of galaxies undergoing mergers. The interaction between merging galaxies isn't a smooth process. It's often marked by disruptions and distortions that tear apart the gas, stars, and dust within each galaxy. This violent interaction helps fuel the central black hole, as gravitational forces stir up the gas and push it toward the core. The more disrupted the merger, the more material gets funneled inward, fueling the black hole at an accelerated rate. This feeding frenzy leads to the peak of quasar activity, which often occurs during the later stages of the merger, when the galaxies are nearing full coalescence. It's during these late stages of merging that quasar activity reaches its most intense phase. As the two galaxies' cores come closer and closer together, the supermassive black holes at their centers engage in a gravitational dance, eventually merging into a single, even more massive black hole. This merging process supercharges the quasar, causing it to release immense amounts of energy, which can be detected across vast distances. The activity around the black hole creates high-energy jets and winds, often accompanied by the brightening of the quasar to its most luminous state. One of the defining features of galaxy mergers is the way they contribute to the growth of supermassive black holes. As gas funnels toward the center and feeds the black hole, it accelerates the black hole's growth, increasing its mass significantly over relatively short periods of time. This rapid growth is often enough to sustain quasar activity for millions of years. The growth of the black hole and the quasar phase are directly linked to the merger process, with more dramatic and large-scale mergers typically producing more luminous and longer-lasting quasars. Quasars are far more common in galaxies undergoing major mergers compared to galaxies in isolation. The gravitational disruption of a merger is often the trigger needed to start the quasar phase, as the chaotic movement of gas and stars funnels the necessary material toward the black hole. Observations of the universe show that quasars are frequently found in galaxies that display signs of recent mergers, such as distorted shapes, tidal tails, and bridges of stars and gas connecting the merging galaxies. These features are telltale signs of the violent interactions that lead to the formation of quasars. Tidal tails, which are long streams of stars and gas pulled out of galaxies during a merger, are one of the most striking visual signatures of these interactions. These tails often carry material away from the core, but they can also direct gas inward, fueling both star formation and quasar activity. The gravitational forces during a merger not only shape the visible structure of the galaxies, but they also provide the black hole with a steady supply of gas, further feeding the quasar. The powerful outflows generated by quasars during a merger can have a profound impact on star formation within the merging galaxies. These outflows can blow away or heat the gas, effectively cutting off the supply needed to form new stars. In some cases, this feedback suppresses star formation, particularly in the central regions of the merging galaxies. By regulating the rate of star formation, quasars influence how the merged galaxy will evolve over time, ensuring that the gas supply is not completely exhausted in the chaotic aftermath of the merger. Mergers can also make quasars more visible by clearing away dust and gas that would otherwise obscure the light. The gravitational interactions between the two galaxies can stir up gas and blow away dense clouds of material, providing a clearer view of the central quasar. This enhanced visibility often makes quasars in merging galaxies appear brighter to observers on Earth, allowing astronomers to study these objects in greater detail. The clearing of dust not only brightens the quasar, but it also allows its jets and outflows to escape more easily, contributing to the large-scale impact that quasars have on their surroundings. In the grand cosmic dance of galaxy mergers, quasars represent a brief but powerful phase in the life of a galaxy. The intense forces unleashed by the collision of galaxies fuel the growth of supermassive black holes, trigger starbursts, and light up the universe with the brilliance of quasars. Through this process, galaxies are reshaped, black holes grow, and the universe's most powerful forces are unleashed, all driven by the gravitational forces that govern these massive mergers. Quasars serve as beacons, lighting up the distant universe and revealing the hidden structure of the cosmic web, a vast network of galaxies, gas, and dark matter that forms the framework of the universe. Their light travels across billions of light years, passing through the tenuous intergalactic medium. As it moves through this cosmic expanse, the light interacts with hydrogen clouds, absorbing specific wavelengths and leaving behind telltale absorption lines in the quasar spectrum. These absorption lines act as cosmic fingerprints, allowing astronomers to trace the presence and distribution of hydrogen gas, revealing the otherwise invisible filaments of the cosmic web. By analyzing the spectra of quasars, astronomers can create detailed maps of hydrogen clouds scattered throughout the universe. These hydrogen clouds are not randomly distributed. They follow the large-scale structure of the universe, clustering along filaments of the cosmic web where galaxies also tend to form. Through this mapping, quasars become indispensable tools for understanding the layout of the cosmos, allowing scientists to study the intricate network of gas and galaxies that spans across space and time. The structure revealed by quasar light shows a universe that is not uniform, but rather woven together by these delicate, gas-filled threads that stretch across hundreds of millions of light years. The distribution of dark matter, which makes up most of the universe's mass but remains invisible to direct observation, can also be traced using quasars. Since dark matter influences the formation and evolution of the cosmic web, the patterns of hydrogen absorption that quasars reveal are strongly influenced by dark matter's gravitational pull. By studying where these hydrogen clouds cluster, astronomers can infer where dark matter is concentrated. Quasars, therefore, offer a window into understanding dark matter's role in shaping the large-scale structure of the universe. Gravitational lensing, where the light from a quasar is bent by massive objects like galaxies or clusters of galaxies along its path, provides additional insight into the distribution of mass in the universe. When the light of a quasar is lensed, it is magnified and sometimes split into multiple images. By studying how the light is bent, scientists can estimate the mass of the lensing objects, which often include dark matter. This phenomenon helps refine models of mass distribution, particularly in regions where dark matter plays a dominant role, offering another way in which quasars aid in probing the cosmic structure. The absorption lines in quasar spectra, especially those associated with hydrogen, also reveal the intricate details of the cosmic web's filaments. These long, thin structures are where galaxies and intergalactic gas collect, but they are incredibly faint and difficult to observe directly. Quasars act as backlights for these filaments, with their absorption lines revealing the existence and location of these delicate threads that link galaxies together. Without the light from quasars, the cosmic web would remain largely hidden from view, its structure elusive despite being one of the most fundamental components of the universe. The light from quasars also provides a glimpse into the distribution of galaxies and gas on an immense cosmic scale. As quasar light passes through different regions of space, it interacts not just with hydrogen, but also with heavier elements in galaxies themselves. This allows astronomers to chart the locations of galaxies and the gas surrounding them, building a comprehensive picture of how matter is distributed across the universe. By observing many quasars across different parts of the sky, scientists can piece together the large-scale structure of the universe, tracing the connections between galaxies and the vast reservoirs of gas that fuel them. In addition to mapping structure, quasars help probe the universe's baryon content. Baryons, which are particles like protons and neutrons that make up normal matter, are scattered throughout the cosmic web, often in the form of diffuse gas in intergalactic space. The light from quasars interacts with this gas, and the absorption lines it leaves behind provide a way to measure the amount of baryonic matter in the universe. This measurement is crucial for understanding the composition of the cosmos and for confirming predictions from cosmological models about the total amount of matter in the universe. Quasars are also key tools in measuring the universe's expansion rate. As the light from quasars passes through the expanding cosmic web, it carries with it information about how the structure of the universe evolves over time. By analyzing quasar light across different redshifts, scientists can observe the growth of the cosmic web and calculate how quickly the universe is expanding. This method complements other techniques for measuring cosmic expansion, such as studying distant supernovae, and provides a more detailed understanding of how the large-scale structure evolves over time. Furthermore, quasars offer critical insights into the early formation of the cosmic web. Some of the most distant quasars, whose light has traveled billions of years to reach us, reveal what the universe looked like when it was only a few 100 million years old. During this period, the cosmic web was just beginning to form, with the first galaxies and clusters of gas starting to emerge from the smooth distribution of matter created by the Big Bang. By studying these early quasars, astronomers can witness the formation of the cosmic web, observing how the first filaments and nodes of gas coalesced into the structures that would eventually give rise to galaxies and clusters. Through their extraordinary light and powerful interaction with the surrounding universe, quasars have become indispensable tools in exploring the vast and complex structure of the cosmos. They illuminate the hidden threads of the cosmic web, reveal the distribution of dark matter, and allow scientists to map the universe on scales that would otherwise be impossible to study. Each quasar acts as a distant but bright probe, offering a way to decode the structure, composition, and evolution of the universe itself. Quasars and active galactic nuclei, AGN, are both extraordinary cosmic phenomena driven by supermassive black holes at the centers of galaxies, but they have distinct differences that set them apart. Quasars, considered a subtype of AGN, are much more luminous, often outshining their entire host galaxies. The reason for this immense brightness lies in their extreme levels of energy output, primarily caused by intense accretion processes, where gas and dust fall into the supermassive black hole, creating an energetic disk that radiates across the electromagnetic spectrum. In contrast, many AGNs, while also powered by supermassive black holes, exhibit less intense accretion and therefore lower luminosity. This means that their energy output, though still impressive, is not as overwhelming as that of quasars. When looking at the electromagnetic emissions, quasars tend to dominate the spectrum, emitting across a wide range of wavelengths from radio waves to X-rays and beyond. This is what makes them some of the most luminous objects in the universe, especially visible at large distances. AGNs, on the other hand, can vary in their emissions, with some being quite strong in certain parts of the spectrum, like radio galaxies which emit in the radio wavelength, while others, such as Seyfert galaxies, have more moderate emissions, allowing the host galaxy to remain visible alongside the active nucleus. The diversity of AGNs makes them appear in both local and distant galaxies, whereas quasars are predominantly observed at high redshifts, indicating that they are more commonly associated with the early universe. A major distinction between the two also lies in their radio emissions. While many quasars are strong radio sources, giving rise to the term radioloud quasars, not all AGNs share this trait. In fact, a significant number of AGNs, especially Seyfert galaxies, are radio quiet, meaning they do not produce the same level of radio wave emission. This radio loudness in quasars is often linked to powerful jets that spew out material at nearly the speed of light, another signature of the extreme conditions near their black holes. Despite the immense brightness of quasars, both quasars and AGNs share similar fundamental structures. They each harbor an accretion disk formed from material spiraling into the black hole, surrounded by clouds of gas and sometimes energetic jets. However, in quasars, the accretion process is generally much more intense, leading to higher energy release and more dynamic outflows of matter. These outflows in quasars can be incredibly powerful, shaping their surrounding environment, while AGNs, particularly those with lower luminosity, may have less dramatic effects on their host galaxies. In terms of classification, AGNs come in various forms, including Seyfert galaxies, which are less luminous but still active, radio galaxies, which are often powerful in radio emissions, and quasars, the brightest of the bunch. This classification depends largely on the energy output and the way the AGN interacts with its surroundings. Quasars, often found in galaxies undergoing mergers or interactions, are thought to be triggered by these dynamic events, which funnel gas towards the central black hole and ignite the intense accretion that characterizes a quasar. AGNs, however, can exist in more stable galaxies, where the accretion process is less intense but still sufficient to power the active nucleus. One of the most remarkable aspects of quasars is their ability to outshine their host galaxies entirely. In many observations, the light from a quasar is so bright that the galaxy it resides in becomes nearly invisible, overwhelmed by the quasar's radiance. This is in stark contrast to many AGNs, where the active nucleus, while luminous, does not completely overshadow the host galaxy, allowing astronomers to study both the galaxy and the AGN together. The human fascination with quasars often stems from this extraordinary ability to eclipse entire galaxies, a reminder of the sheer power locked in the centers of these distant objects. Ultimately, while both quasars and AGNs offer a glimpse into the extreme environments surrounding supermassive black holes, quasars represent the most energetic and dramatic examples, often reflecting the chaotic processes of galaxy formation and evolution. AGNs, though less intense on the whole, are still fascinating in their diversity and provide insight into the more subtle, yet equally important, mechanisms at play in the universe's most powerful cosmic engines. Quasars are some of the most astonishing and powerful objects in the universe. Despite being relatively compact in size compared to galaxies, they shine with an intensity so immense that they can completely outshine the galaxies in which they reside. What makes them particularly remarkable is that their energy comes from supermassive black holes at the centers of galaxies millions or even billions of light years away. These black holes are unimaginably massive, with millions or even billions of times the mass of our Sun. The brilliance of a quasar is created by the enormous amounts of gas and dust swirling around the black hole in what's called an accretion disk. As this material spirals inward, it's heated to extreme temperatures, millions of degrees, by friction and the immense gravitational forces. This process releases an incredible amount of energy, which radiates out as light, X-rays, and other forms of radiation, creating that iconic, almost blinding luminosity we associate with quasars. One of the most fascinating things about quasars is how far away they are. When we look at a quasar, we're seeing light that left it billions of years ago, essentially looking back in time to the early universe. They offer a window into a period when galaxies were still forming and evolving. But quasars aren't just interesting for their brightness or distance. They had a profound impact on the galaxies they inhabit, shaping them with their intense radiation and gravitational forces. In many ways, quasars are not just isolated phenomena. They're part of the larger story of how the universe and its galaxies developed over time. Their existence reminds us just how dynamic and interconnected the cosmos really is. As we wrap up our journey through the fascinating world of quasars, I hope you've gained a deeper appreciation for these cosmic powerhouses and the role they play in shaping the universe. From their early formation to their mysterious connection with supermassive black holes, quasars continue to be one of the most compelling subjects in astrophysics. Whether they're helping us understand galaxy evolution or serving as cosmic lighthouses guiding our gaze into the distant past, quasars offer endless mysteries to explore. Thank you so much for watching this episode of Quiet Universe. If you enjoyed learning about quasars, don't forget to hit that like button. It really helps us reach more curious minds. And if you're ready for more deep dives into the wonders of the cosmos, make sure to subscribe and ring the bell so you never miss our next journey through the stars. Stay curious, and I'll see you in the next one.